Okay, hi everybody, it's Samantha. I'm one of your guys' SIs for Chem001C. I SI for Dr. Dian Zhang, and my office hours are Monday 10 to 11, Thursday 11 to 12 p.m. If you have any questions, feel free to drop in during office hours, comment in the section down below, or even shoot me an email. So with that, let's get started. We're going to continue with acid-base chemistry, and today we're going to focus on buffers. Dr. Jang covered buffers on Friday and on Monday. And with that, well, what is a buffer? With buffers, a buffer range is a pH range where a buffer, an acid-base pair, can provide pH protection. So if a strong acid or a strong base were to be added to a solution that's a buffer, your pH won't change very much, because when it's a strong acid that's added, the acid is going to react with the weak base that's in your buffer. And when it's a strong base that's added, the base is going to react with the weak acid that's in your buffer. That interaction with your acid-base pair provides pH protection so that the pH of your solution won't change drastically. Now, let's get mathy with it. How does that actually look with math? Well, with that, you're going to look at your Henderson-Hasselbalch equation, and that is essentially pH equals pKa plus log of base over acid. Now, I put that here in two different ways, verbally, where it's just base versus acid, or with what you will tend to see is something with less H's, less protons, and something with more protons. So your acid, as we remember with the Bronsted-Lowry definition, your acid is going to donate a proton, so it's going to have more protons. And that's going to come in handy when we get into our discussion question. Now, if you look at it, if your base over acid is a 1-to-1 ratio, it's going to give you a 1. And in that case, log of 1 is 0, so your pH is equal to pKa. Now, what happens if you have more acid than a base? Well, then your pKa is going to be less than your pH. And if you have more base than you do acid, then your pH is going to be less than your pKa. Your pKa is going to be higher, right? So all that this is saying is essentially, when you have more acid, you're going to have a lower pH. If you have more base, you're going to have a higher pH. Now, I'm going to go over a question that Dr. Jang went over in class. I noticed a few people during my office hours yesterday, or on Monday, sorry, were struggling a little bit with this. And it was, what is the pH of the HPO4 2- H2PO4- buffer solution, given the concentrations are 1 molar for both, and that you have a pKa1, pKa2, and pKa3 for H3PO4. Well, if we look at this, what's important to note is we have a polyprotic acid, right? We have H3PO4. Well, a polyprotic acid is going to dissociate. It's going to lose all 3 of its protons. When it loses all 3 of its protons, we're going to have 3 different pKa's. Now, if you look at the relationship, it goes from H3PO4, it's going to lose a proton, and then it becomes H2PO4, and that's also going to lose a proton, and for it to become HPO4 2-. HPO4 2- is also going to lose its proton, and it's going to become PO4 3-. Now, these 3 relationships we know are going to become pKa1, pKa2, and pKa3. It's easiest for it to lose a proton here, and it becomes slightly harder here, and even more difficult to lose that proton here. So we know pKa1, pKa2, and pKa3 correspond to those reactions accordingly. So knowing that we're looking at HPO4 2- and H2PO4, which pKa would we use for our Henderson-Hasselbalch equation? In this case, because we're looking at HPO4 2- and H2PO4-, we're going to be looking at our pKa2, right? So we're going to be taking 7.21. And if you remember from the previous slide, it's pH equals pKa plus log of base over acid. Now, what's behaving as our base and what's behaving as our acid? If you remember what I said earlier, the acid is going to have more protons, right? Because it has a proton to donate. So between these two, H2PO4 is our acid and HPO4 2 minus is our base. Now, it's a 1-to-1 ratio, so it's log 1. So if that's the case, we know pH is equal to pKa, and pH, when you do the math and calculate, is 7.21. So this is only one of the questions that a few of you guys found difficult. Let's go even deeper with this concept of buffers, right? So the second question is, what's the final pH under the different conditions, and how does the buffer, we're going to use HPO4 2 minus and H2PO4 minus, again, how does that behave as a buffer? Well, if we look at it, we have 990 milliliters of our buffer solution, and these are the given concentrations that we have to use. And we have 990 milliliters of pure water, right? So we know that if that's the case, when you do calculations with the pKa and everything, your initial pH is going to be 7 for both your buffer and your water. That's given to you, right? Now, what happens if you add 10 milliliters of a 1 molar HCl, that's an acid, and what happens when you add 10 milliliters of a 1 molar strong base, NaOH? What's that going to do to your water, and what is that going to do to your buffer solution? Well, let's start off with our water, okay? So with our water, the best way to do a calculation here is to do a C1V1 equals C2V2 calculation, right? And why is that? Well, for us to calculate pH, if you don't remember, pH equals negative log of the concentration of H. When you do C1V1 equals C2V2, you're able to obtain directly the concentration of H in your new mixture, right? So if let's go back. If the 10 milliliters and the acid is our initial condition, right? That's our C1V1, 0.01, and remember to do your calculations in the right units. Here it should be in liters times molarity, because that's moles over liters. That's 0.01 times 1 over 0.99 plus 0.01. Why? Because, well, our new volume is water and the HCl, and in that case, the new volume is 1 liter. But what is our concentration of H? We're calculating for that C2, and here we get 0.01, and you can calculate your pH that way. A similar logic is going to be applied when we find the pH for NaOH. But remember to be careful, because now you're working with NaOH. You can still find pH, but remember you have to use the right formula and find your pOH first, and then remember that relationship between pOH and pH. When you do those calculations, you end up having a pH of 2 and a pH of 12 respectively. Okay, now moving on. From here, we can now calculate what actually happens to our buffer, right? And this is where we're going to see why and how H2PO4 minus and HPO4 2 minus, our acid and our base, why those acid and base pairs behave as a buffer. Well, to be able to find our pH, how can we actually do that? We want to find the concentration of H, right? But we can't directly do that by doing a simple C1 V1 equals C2 V2. Why? Because the changes that occur aren't going to necessarily be proportional. So what have we learned that actually allows us to do that? Well, we can look at a rice table and see how the changes influence the amount of moles and ultimately the concentration in our buffer. So when an acid is added, we know that the acid interacts with the weak base. So if that's the case, this is going to be our reaction, right? It's going to be our acid, the proton, H+, plus our weak base equals our acid, right? So the acid is added, interacts with our weak base, and we get the acid pair that pairs with the weak base, right? So we do a rice table and we put that in and we find our initial conditions, right? Our initial conditions, we want to look at our moles first, right? Because we want to know what happens to the moles in our reaction. So we take our initial conditions from this slide right here, and we plug it in accordingly, right? So 0.01, we have 0.01 moles of our H plus, we have 0.61 moles of our HPO4 2 minus, and 0.99 moles of our H2PO4 minus, right? Now, because we know that the H is added, with the change that occurs, we're going to look at our H. That change on this side, because that H is going to get used up, is minus 0.01. It matches to the 0.01 here. And we're going to put that through the entire rice table, right? We remember how to fill out our rice tables. And that's going to be minus 0.01 plus 0.01, and that's going to give us our equilibrium value. Well, that equilibrium value is currently just in moles. We want to find the concentration, right? We need the concentration to be able to figure out our pH. And in this case, we're going to look at that mole, and we know that the total volume of liquid we have is 1 liter because it's the 0.990, the 990 milliliters of the water and the 10 milliliters of the added acid. So 1 liter. And in that case, it becomes 0.60 molarity and 1 molarity. And then to find the pH, we just plug that into our Henderson-Hasselbalch, and we get 6.99. If we were to repeat that with the base added, we repeat the same logic, but now this time we have to remember a base is now added. And if a base is added, the base reacts with our weak acid. Now that will give us this reaction, and if we were to fill that into our rice table, it would be as follows. Another important thing to note here is, remember, we're not going to look at H2O because H2O is a liquid and it's not aqueous like the rest of this, so it's not going to be involved in our reaction. It would skew our results if we were to add it, right? So now we're going to look at what we have here, and remember, H2PO4 minus is our acid, HPO4 2 minus is our base, and when we obtain the molarity, the concentration, we can plug that into our Henderson-Hasselbalch equation once again, and that's how we get 7.01. Now, if we go back to the table we were supposed to fill out, now it's all filled out. And now we see that the pH went from 7 to 6.99 when an acid is added, and then 7 to 7.01 when a base is added. Now, this is where you're able to see, because this is a buffer, H2PO4 minus and HPO4 2 minus, that's a buffer. When a strong acid and a strong base is added, because it's a buffer, the pH is somewhat protected. It doesn't change drastically. That's it for buffers. If you guys have any other questions, comment down below or email me, or even feel free to drop into one of my office hour sessions. And please don't forget to sign in using the link in the description.